In this video, we're going to talk about what valence electrons are, how to write an electron-dot symbol, and a few trends in periodic properties in the periodic table. So first of all, valence electrons. The valence electron is any electron in an atom that's in the highest occupied level. That is, all the electrons that have the highest N that's occupied. For example, in sulfur here, the electron configuration for sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. The highest level, or the highest N that has electrons, is the N equals 3. And the 3s and the 3p electrons are all valence electrons, so there's 2 plus 4 is 6 valence electrons in sulfur. Now in niobium, its electron configuration using core notation is krypton 5s2, 4d3. Well, even though we put the 4d electrons in last, the highest N, or the highest level that has electrons, is the N equals to 5 energy level. And so these two 5s electrons are the only valence electrons. So niobium only has 2 valence electrons. Now, for the representative elements, remember that's the first 2 columns, alkali metals and alkali earth metals, and from boron over here through the noble gases, these block here, you can look at the periodic table and just tell how many valence electrons they have. Everything in the first column has 1 valence electrons, 1. Everything in the second column has 2 valence electrons. Skipping the transition metals, everything here in the 3A has 3 valence electrons, 4, 5, 6, 7. Now here, helium only has 2 electrons total, so helium only has 2 valence electrons. Otherwise, every noble gas has 8 valence electrons. In terms of the transition metals, most of those only have 2 valence electrons because the highest occupied N will be the 4s for here, the 5s for here, 6s and 7s and so on, because these are 3d, 4d, and so on. Except watch out for the exceptions. Remember, chromium is 4s1, 3d5, so there's only 1 valence electron for chromium. Likewise for copper, 4s1, 3d10. Electron-dot symbols, all they are is writing the symbol for the element, and for every valence electron, put a dot. Now, usually we only put no more than 2 dots per side, but other than that, you can arrange them any way you want to. Imagine that there's a square around the symbol. There's 4 sides, each side can have no more than 2 dots. Sulfur has 6 valence electrons, so you could write them 2 here, 2 here, 2 here, 2 here, 2 here, 1 here, 1 here, or any other arrangement that gives you 6 dots, no more than 2 to a side. Calcium has 2 valence electrons. It's an alkaline earth metal. It's in the second column, so either like this, or 2 up here, or however you like. Now, periodic trends. The size of the neutral atoms, okay, the atomic size, or the atomic radius. Okay, what this is, it's basically how far out from the nucleus the outermost electrons can extend, or do extend. And the trend in the periodic table, this is basically what you have to know about at this point about atomic size or atomic radius. And that is that the atoms get smaller in general as you go up and to the right in the periodic table. So following this trend, helium would be the smallest. Francium would be the largest. Now there's some minor exceptions, but you don't have to really know those. You don't have to know those. Okay, just know the trend. Atomic size or atomic radius decreases, gets smaller up and to the right in the periodic table. The next trend is called first ionization energy, and this is how much energy it takes to remove a valence electron from a neutral atom. So sodium, this is the electron-dot symbol for sodium. Sodium has 1 valence electron. If we take that electron away, now we're left with 1 more proton than we have electrons, right? Because neutral sodium starts out with 11 electrons. If we take 1 away, it still has 11 protons, but only 10 electrons and has a positive charge overall. We'll see this in a little bit. And so we remove the electron. This process, the energy required to do this is called the first ionization energy. Now, really all you need to know about this at this point is that it increases as you go up and to the right in the periodic table. It gets harder to remove an electron as you go up and to the right. So it would be hardest to remove an electron from helium and easiest from francium. Metallic character is the next periodic trend. This is how much it acts like a metal. What do metals do? Well, they tend to be shiny, tend to be able to bend them, pull them into wires. They conduct electricity, they conduct heat. And the more something acts like a metal, the more metallic character it has. And you can see this in the periodic table. Remember this line right here? Remember, to the left of that are metals, to the right are nonmetals. So you could probably guess that it's the elements are more metallic as you go to the left and less as you go to the right. And so the trend as you go up and to the right is that metallic character decreases in the periodic table. Helium is the least metallic. Francium would be the most metallic. So, if we wanted to arrange the following elements, selenium, germanium, and chlorine, in order of increasing atomic radius, first ionization energy, and metallic character, it would look like this. Because radius gets smaller as you go up and to the right, if you look at a periodic table, you see that chlorine is up and to the right the most, so it's the smallest, selenium's in the middle, and then germanium is the largest. First ionization energy increases as you go up and to the right, so chlorine would have the highest first ionization energy, germanium the lowest. We go germanium, then selenium, then chlorine. Metallic character decreases up and to the right, so chlorine is the furthest up and to the right. It would have the least metallic character, then selenium, and the most metallic of these three would be germanium.